Welcome, everyone. Just briefly, my conflicts of interest. I don't think I have any conflicts of interest. The research that I will present was funded by the Research Triangle Institute International and the Agency for Healthcare Research and Quality. So just a quick overview. Over the next probably 30 minutes, I'll talk about the use of large language models for data extraction in evidence synthesis. I'll start with some background on data extraction and then touch on how AI and large language models have been used in this context. And I'll present research findings of a study that we conducted, and then I'll finish with some practical guidance for anyone interested in using a large language model for data extraction. So data extraction, as you know, involves transcribing data from primary studies into standardized tables. And data extraction varies in complexity. Sometimes it is really just copying and pasting, but sometimes it requires more complex tasks like transformations of data or simple calculations. And if you haven't done it for a while, data extraction is time consuming, it's tedious, it's error prone, and pretty much everyone hates to do it. Sorry. The risk for mistakes is really high for data extraction. So a method study showed that up to 50% of studies in systematic reviews have at least one data extraction error. There are basically three ways to do data extraction in reviews. The simplest approach is when a single person extracts data and nobody else checks it. So single reviewer data extraction. And the risk of errors then is high, really high. The most commonly used method involves a single person extracting data with another reviewer checking it afterward for accuracy and completeness. But errors still occur in about 16 to 24% of data items in the published studies, so method studies that looked into this. The most rigorous and accurate method is dual independent extraction, where two reviewers independently extract data and then reconcile the discrepancies. And in general, what you can see from these numbers is that humans are really not good at extracting data and not a very good gold standard. Messier, so the Cochrane standards, state that dual independent extraction is mandatory for outcome data and highly desirable for all other data. The idea of using AI to assist data extraction is really not new. Previous methods mostly relied on natural language processing using statistical models such as Bayesian models or support vector machines. And all of these approaches required large amounts of labeled training data and still often didn't achieve sufficient accuracy. And particularly, they often really struggled with data extraction from tables and figures. Now, sorry. The advent of large language models has fundamentally changed this landscape. These language models are trained on vast amounts of data to predict the next word in a sequence of words or tokens, so like a sentence. And the big advantage of these LLMs is their capability for this known as zero-shot applications, meaning that they don't require a specific training data or programming to extract information. And over the past few years, these LLMs have also made remarkable gains in speed and in their ability to process large volumes of text. And This development, the large volumes of text, is really important for us as reviewers, because in data extraction, we usually work with PDF documents. So that means we must be able to upload entire PDFs to an LLM for extracting data. And this capacity varies across models. So what you can see here in this table are some examples. The free version of ChatGPT, for example, can handle around 8,000 what is called tokens, so which translates roughly to about 11 pages of a PDF document. So enough for some papers, but probably not enough for a publication with supplemental materials. DeepSeek, on the other hand, already has a much larger context window, allowing uploads of about 85 pages, Claude Sonnet about 265 pages, and Gemini 1.5 Pro offers a really large context window for around 1,300 pages of PDF documents. Several studies have validated the use of large language models for data extraction from full text PDFs, and they reported accuracies that ranged between 72 to 100% compared to human reference standards. This sounds very promising, but there are also substantial limitations of these studies. They were all conducted in sort of controlled settings using pre-existing review data sets as benchmarks, which really may limit the generalizability to real-world systematic reviews, real-world scenarios. Additionally, all of these studies primarily focused on fully automated approaches without the human involvement in the data extraction workflow. And I'd like to quickly talk about one of these validation studies as an example. So last year, we conducted a proof of concept study using Claude, so a large language model developed by Anthropic. And our main goal was simply to see whether the large language model could, in principle, perform data extraction effectively. And we tested Claude on 10 randomized controlled trials of pharmaceutical interventions, asking it to extract 16 commonly used data items. But we selected the data items very specifically so that the large language model had to locate the information from different parts of the journal articles, such as text, tables, and graphs. And this was important because automated data extraction, as I mentioned before, has historically struggled with pulling accurate data from tables and graphs. And on this small study, we thought the results were really remarkable. So Claude achieved a 96.3% accuracy. It made only 6 mistakes out of 160 data extractions. 4 times it missed data. There was one major error where it fabricated data, so what is called a hallucination, and one minor error which was just a rounding mistake in a standard deviation. And it also detected several errors in the human data extractions. And some of the data items we asked Claude to extract were really straightforward. So for instance, the trial registry number, which just involves transcribing data from the publication into the table. Others, however, were more challenging, like the count and the proportion of female participants, which required pulling data out of a table. And in this particular case that you see here, this was even trickier because the original study didn't report the proportion of females, but instead reported the proportion of males. But Claude still managed to accurately calculate the number of female participants and the associated percentages, which we thought is actually really impressive. And so we went back and we asked Claude, how did you get there? How did you calculate the number of female participants? And it gave us a very clear explanation. It said, I took the number of male participants from the table, and then I subtracted that from the total number of participants. And to calculate the percentages, I divided the number of female participants by the total number and multiplied by 100. And this goes far beyond simple data transcription. So it's actually a form of reasoning that happened here. And so for us, this was a clear indication that large language models might have a real potential for data extraction. But as I mentioned earlier, all of these controlled validation studies have significant limitations. And the most important being that they are not conducted within the workflow of an actual real-world systematic review. And to address these limitations, we designed a larger study to assess Claude then under real-world conditions. And this study was designed as a SVAR, so a study within reviews, and it involved 6 ongoing systematic reviews of the US Agency for Healthcare Research and Quality. And the focus now was on comparing 2 different workflows for data extraction. So the traditional human-only approach, where one person extracted data, the other one checked for accuracy and completeness, versus a semi-automated approach where we replaced one human with Claude, and Claude took over the initial data extraction. And our outcomes of interest were the concordance between the 2 approaches, the accuracy of the semi-automated approach, and also the time required for data extraction for each approach. And the study had a prospective parallel group design. For each systematic review, the investigators formed 2 teams. So one team conducted the traditional human-only data extraction, while the second team used Claude for the initial data extraction, and then a human investigator checked the correctness of Claude's work. And the 2 teams extracted exactly the same data elements, but they were blinded to each other's work. And after both teams had finished extracting data, their results were sent to an independent adjudication team. And this team was also blinded to which workflow each set of the data came from. And the tasks of the adjudicating team was to compare the data extractions, and for any discrepancies between the 2 data extractions, the adjudicators went back to the original journal articles to verify which one was correct. But as you know, data extractions are rarely identical, so there are always some differences even between human researchers. But these differences don't always mean errors. So sometimes they're just differences in the level of detail. And to handle this, we developed a definition of concordance to help us determine whether there was an actual error actually or not. And we defined concordance as the factual congruence of extracted data items, even if there are variations in style, presentation, or length between the 2 data extractions. The adjudicators also classified the severity of errors in 3 categories. A major error meant that the mistake could seriously compromise data accuracy and could potentially lead to wrong conclusions. A minor error was less severe, like a rounding mistake. And finally, there were so-called inconsequential differences. So for example, if the level of detail in reporting was different. So the study has not been published yet, but I'd like to give you a quick preview of our findings. So overall, the 6 systematic reviews included 63 studies, both randomized controlled trials and non-randomized studies of interventions. And all 6 reviews together extracted more than 9,300 data items. And this slide summarizes our key findings. So concordance between the 2 data extraction methods, which is shown here on the slide in purple, was 77%. So not very good, but we have to keep in mind that concordance is affected by errors in both methods. Probably more interesting is the comparison between the AI-assisted approach and the human-only data extraction approach. So overall, the AI-assisted method slightly outperformed the human-only method. Accuracy was 91% for AI-assisted versus 89% for the humans, while recall was 89% compared to 86%. And precision was essentially identical between these methods. And recall in this context refers to the ability to correctly extract available data. So missing data or incorrectly extracting data lowers recall. And precision measures how correct the extracted data items are, regardless of the missed data. We did not perform any formal statistical tests, but if you look at the confidence intervals for accuracy and recall, they do not overlap. So had we conducted formal hypothesis testing, these differences likely would have been statistically significant. It's also really interesting to look at the proportion of mistakes, of errors that the 2 teams made. In this slide, we distinguish between major errors, so errors that are serious enough to potentially lead to incorrect conclusions, and then any incorrect data extractions. The proportion of major errors was almost the same between the 2 methods, 2.5% versus 2.7%. However, when considering all incorrect extractions, the AI-assisted approach again performed slightly better with 9% versus 11% for the humans. And if you think back to the beginning of my presentation, I showed you a slide with the proportions of data extraction errors reported in the literature. And for single data extraction with verification, it ranged from 16% to 24%. And so the humans here in this study actually did really well with 11%. So these were all professional systematic reviewers from these evidence-based practice centers. But still, the AI-assisted approach was slightly better. The most frequent errors that both approaches made was that they missed available data. So the percentages here are out of all extracted data items. So the humans missed 6.5% of available data out of all 9,300 data items. Less common mistakes included misallocated data and incorrect calculations. And rarely we encountered cases of fabricated data. So we classified data as fabricated if we could not locate it anywhere in the original publication. And in such cases, we assumed the data was either generated, so hallucinated by the AI, or of whatever unknown origin for the human extractors. And as I mentioned in the beginning, we were also interested in the time on task. So On average, the AI-assisted method was notably faster, except in one review, so that is peripheral nerve blocks. But overall, it took the AI-assisted teams 41 minutes less per study to extract compared to the human-only approach.